So I have the pleasure of introducing our colleague and faculty member, Achin Ramilk. Achin has been working with our department for a number of years now, very closely, both as a professor in the department and teaching a major course, which he and I do every fall, on augmenting the human senses with bioscience and technology. Any of you who have time mid-morning to noon on Fridays throughout the fall are welcome to join us. Happy to share the class schedule. So Achin is a PhD engineer. He rose to become vice president in Intel of perceptual computing. Before, we were very fortunate that a very forward-looking, research-oriented company looking at technology development, Starkey, brought him as chief technology officer some seven years ago now. And he has committed to modernizing hearing aids, to incorporating artificial intelligence, and to adding many functions beyond merely helping hearing. Biometric monitoring, monitoring of sentiment, monitoring perhaps of cognitive decline. And he has been a co-investigator in a research program with Kristen Steenerson now, as principal investigator, on using accelerometer enhanced hearing aids to detect movement patterns that predict the possibility of a fall. And we'll hear more about that, I suspect, today. But Achin, thank you very much for joining us and educating us on a very hot topic of artificial intelligence.
Thank you. Good morning, everybody. Bright and early. So this talk I was supposed to give last December, but I fell sick at the time. I think it was flu or something like that. So I did update a little bit. Field of generative AI has moved very fast. But it's such an exciting area and just so much time could be spent talking about it. I did have to pick and select what I talk about. So today, you're not going to hear much about how we are using AI in hearing devices. It's a significant part of the class that Rob and I will teach this fall. And if there is a lot of interest, that probably is more than an hour of talk in itself, I'll be happy to come back later to just focus on how we are using this technology that we'll talk about today in hearing devices. But I'm not going to get too much into the details. The intention of this talk was just to have a discussion here about generative AI in principle, this technology that pretty much has caught fire over the last few years since the introduction of ChatGPT, right? Let me get a quick show of hands. How many of you used ChatGPT or Claude or Gemini at least once? At least once? Okay, almost all of you. How many of you used in the last month at least once? Last week at least once? Yesterday at least once?
And how many of you paid for it, right?
How many of you paid? Yes, $20 a month. Yeah, quite a few of you. Let me see another show of hands. How many of you think you use AI every day without even noticing it, paying attention to it? Everyone, right? Where do you use it? It's every time you're using Outlook or Gmail, the AI is deciding what you should be reading and what should go into the junk folder. You're calling Uber, the map is getting optimized with real-time data and AI analysis. And other areas, banking, your account's keeping safe because of AI looking after spurious attempts to get into your account. It's a whole bunch of ways that AI has impacted our world. But today I'm going to specifically look at generative AI. It's a new branch of AI. And a little bit about my background. I've already said what I do. I'm a student of research in computational perception. I've been working on that for over 20 years, probably 25 years now. So what is computational perception? Essentially for us researchers and engineers, that's learning. It's an intersection of neuroscience and engineering. For us to understand how the human systems sense, perceive, or understand the world around us, and then use that knowledge to build systems, computational systems that can do sensory processing the way, more or less the way the human sensors do. For us, humans are a collection of sensors and processors. Your ear, eyes, touch sensors, and the cerebral cortex. So the engineers would like to see how could we build systems that could be applied to intelligent computers that would hopefully be able to sense and understand the world like humans do. And then I divided into two areas. When I was at Intel for 17 years, and I was vice president of the group I created, I called that perceptual computing group. There were 1,600 people. The focus was entirely on adding sensing and understanding with neural networks and AI, other types of AI, into the processor and the systems, so you can enable natural human-computer interaction. So what are those computers? Not just your laptops or desktops or tablets or phones, but those are robots, drones, virtual reality headsets, the world where technology and human interact with each other. So as Rob mentioned, 7 years ago, I took a dive into medical devices. For the last 7 years, my focus primarily has been an element of that, which is to help augment human senses. How can we sense and understand the world better with help from additional sensors and the use of machine learning and AI? And this slide I always show in my class and whenever I'm presenting on AI, because very early in my career, this inspired me no end. How many of you have heard about or read about the Dartmouth workshop? Very few. So let me tell a minute about this. Back in 1955, a year before this workshop was held, Professor John McCarthy, he was assistant professor at Dartmouth at the time, pulled together a number of computer science professors. In the middle, we see Dr. Marvin Minsky, unfortunately passed away just a few years ago, who created MIT Media Labs. On the right is Claude Shannon, also was at MIT and considered to be father of information theory. And there were a number of others. So Marvin Minsky was already working on the idea of having computers see and understand the world, and he doubled down after this workshop. But McCarthy pulled these teams together to discuss what he called thinking machines. Thinking machines, they had to come up with a cool name for it. So he gave the term artificial intelligence as a theme for this discussion. So for a couple of weeks, they debated about how this field should go, and they published an essay at the end, and I borrowed a sentence from there. It's an audacious statement, particularly at the time, in 1956. Features of human intelligence can be so precisely described that a machine can be made to simulate it. That inspired a whole bunch of people to pursue this. And of course, you could say that event there in Dartmouth College was the beginning of deeper research, wider research in AI. Many of you probably know McCarthy came to Stanford in 1962, and he co-founded the AI labs here, the famous Stanford AI laboratory. Spent the rest of his career here at Stanford. So topics that we'll discuss today, and I'm going to speed up sometimes and then slow down sometimes to have a discussion. But I do have a lot of content I have to get through. So we'll talk about generative AI, and primarily, I want to introduce you to a new type of architecture that is different from typically AI we used to deal with, like convolutional neural network, recurrent neural network. Those are the AIs that dominated the field for 10 plus years. And recently, this adoption of transformer neural networks, an architecture that researchers introduced only in 2017, but started to get widely adopted only recently, in the last 2 to 3 years. I'm going to show you the architectural details and some mathematics behind it. So hopefully you walk out knowing the details of why so much excitement about this. The discussion part would be, we'll have a bi-directional conversation, hopefully, on motivation. Why do we care here in the room about this? Implications to our field. I will have some interactive modules to try and get a feel for it, and I'm probably getting ambitious for an hour. And then we'll have some discussions about where does it work really well, where is it still failing and have some weakness. And we'll talk about future trends as well. Where are you going from here? Good? All right, so one thing about Stanford, some of you might have read this. In the last few years, Stanford has been publishing this annual report called AI Index Report. The 2024 report just came out, and they did a phenomenal job. It's like 100 plus pages of report with a thorough, detailed look at what's happening in the field of AI around the world. So I borrowed this slide from that. First of all, to point out here, the investment, private investment in the field of generative AI, not AI, just the narrow slice of that is generative AI with transformer neural networks, received $25 billion of investment in 2023, $25 billion, which is 9 times bigger than the year prior, 30 times bigger than 2019. And overall investment in AI was about $100 billion. Just think about how much investment is going into developing this technology. It sounds a little bit like hype to many of us, right? If you just type AI hype, a whole bunch of opinions are about, yeah, it is. There's a lot of hype in there. Who thinks maybe there's a bit of hype going on with AI? Yeah, quite a few of us. So I thought what I'd do, part of the fun element first thing in the morning, so to take you back in history. This is a photograph of 1958 New York Times article. And I'm going to read the beginning of this article. It says, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, and take it, reproduce itself, and be conscious of its existence. So what were they talking about in 1958? It turns out they were talking about this machine, a 5-ton computer that was built by IBM and architected, designed by Dr. Frank Rosenblatt. He was at Cornell University at the time. And this is credited to have been the first machine learning computer system. Here you see young Professor Rosenblatt. And the amazing feat that New York Times got so excited about was this idea that he could train this machine to learn whether punch cards were punched on the left or on the right. So that's the simple task of the machine to know. You feed a punch card and it will say, oh, that card is punched on the left. Or it's punched on the right. Very simple, right? Recognize left or right. But instead of an algorithm that an engineer could easily write and perform the task, he for the first time showed the machine could learn to recognize it. So it was a perceptron computer. And I'll tell you more about the perceptron, essentially copying the architecture of human neuron, but only a handful of them in this machine. There was no transistors back then. And after 50 trials, essentially feeding a punch card, and machine would take a random guess. Rosenblatt would say wrong, or yeah, that one you got right. After 50 trials of just telling the machine right or wrong based on its random output, the machine learned to accurately and correctly tell you whether the punch cards were punched on the left or the right. So that simple ability to learn and perform excited New York Times no end, right? That was back in 1958. So what do you expect? The field should have caught fire, because with all of the investments the government was pouring into this system and others, unfortunately, this was followed by, so this was 1957, excitement around Rosenblatt's perceptron. It followed by a sharp drop in interest in AI. This is sort of like popularity of AI, so it's a qualitative y-axis. By the way, anyone knows about the late 1200s AI? There was no term AI, right? The reverend's name was Raymond Lully in Spain. He built a mechanical system that he claimed was intelligent. And it had 3 circular discs that would rotate, and it would logically deduce stuff. So Raymond Lully started by saying, this system can create your horoscope. So, well, I think, we could, who knows whether horoscope is right or wrong after it takes a long time to understand how accurate it is. So his claim of being able to generate horoscope created the first excitement in intelligent systems. Unfortunately for him, he got really ambitious and he said, this system should be able to also predict crop production. And of course, that you can pretty much in a year or two tell whether how accurate that was. And didn't do very well. And there's the first AI winter, and Rosenblatt's excitement that got dipped, unfortunately, primarily because I showed you the picture of Marvin Minsky. He's one of the father figures of AI. When he went back to MIT after the Dartmouth workshop, his group showed with a single perceptron, which was driving the architecture for the thinking machine, Rosenblatt's machine, could not replicate even XOR function, which is one of the basic logical functions. He actually wrote a book to talk about all of the negative aspects of perceptron, and he ended up creating a push that resulted in a winter in AI. And then in the 1980s, there was another era of symbolic systems and expert systems. And that didn't do as well, and there was a winter. So this graph I took from Dr. Yasnitsky's paper, which he published in 1980. And there he was asking a question: where do you think we're going from here in 2018? 2018. Is it going to keep going up, popularity of AI and adoption of it? Is it going to plateau? Or is there going to be another winter in the 2020 timeframe? What do you think happened? So it's not just it was forecast one, many times over, right? So what is new now? Many of you have read all this stuff. I'm just telling my perspective. There are four things that happened that separates this era from all the other eras that you have seen in AI. Number one, extremely large neural networks. Let's talk about that for a second. Human brain, we have roughly 100 billion neurons. If you say every neuron likely is connected to, let's say, 10,000 other neurons, we know that from the visual cortex, then you could say probably have about 1,000 trillion synapses, about 1,000 trillion synapses. GPT-4 that powers today's ChatGPT has 1.8 trillion parameters. So you're talking about the order of magnitude of neural connections in the system. Unprecedented levels of largeness, bigness in the neural networks. Just was unthinkable just a few years ago. Computing resources. Today we have amazing computing resources. So I spent 17 years at Intel. Intel introduced microprocessors back in 1971. The first microprocessor, called Intel 4004, had 2,300 transistors. NVIDIA just announced their latest GPU. It's got 208 billion transistors on a single chip. 208 billion. Remember human brain, 100 billion neurons? There is a startup company out in the valley that's trying to compete with NVIDIA. They have a wafer scale processor. Name of the company is Cerebras Systems. They just announced a single processor with 4 trillion transistors on them. Even just a few years ago, it would have been a dream for us. So these two are now combining hands. The hardware companies with throwing amazing computing resources, and software engineers are generating these large neural networks with 1.8 trillion transistors. It was a year older. Imagine the next wave of models that are coming out. They're just going to be 10 times more in parameters. Data sets, let me give you a number there. GPT-4 was trained with 13 trillion tokens. Roughly, one word is equivalent to 1.33 tokens. So that means GPT-4 was trained with 10 trillion words. Put that in perspective. And an average human, not an average human, I think humans going to Stanford or equivalent universities and pursuing a career, would be exposed to maybe 500 million words in your life that you'll speak, another 500 million you'll read. So about, let's double that. Let's say 2 billion words. Our neural network in our head is trained with 2 billion words then, actually much less because, I've only probably spent half of my life. So half of that billion words is still ahead of me. So you are getting trained with 1 billion words, and we can perform such an amazing job. This system, GPT-4, was trained with 10 trillion words. So that's what I meant by enormous data sets. And last but not the least is just a technology. For the longest time, we didn't have good, efficient training algorithms to evolve and fully train the neural networks. The adoption of efficient neural network training technology or algorithms, which is called backpropagation, based on gradient descent. All of the neural nets I'm going to show you, they're all trained with this algorithm. Such an efficient way to train systems with data. So these are the 4 things that led to the wave that is like much bigger than many of us imagined just a few years ago on what is going to happen with AI. Even those of us who've been working in the field are totally stunned and surprised with just what we've done. The impact of it. Again, here I'm going to go fast on this a little bit. Let's look at an example. So UC San Diego researchers and Johns Hopkins, they did this project last year with ChatGPT 3.5, not even 4. The 4 is like way more capable. So they took this project where they wanted to see how ChatGPT powered by GPT 3.5 compare with human physicians in responding to questions that patients ask about their health. So they picked 195 questions from social media and other places where patients ask, they want to know about their physical health. And this team of researchers, they took those questions and they got the answers from GPT 3.5. And then they also got answers to those questions by an expert panel of physicians. Then they mixed them up. And then they had another team of expert human physicians to evaluate those responses. And the evaluators, of course, didn't know whether the response came from GPT or came from a doctor. And so they wanted to study how accurate this results from the AI systems are. And here is the conclusion. ChatGPT's responses were more accurate than the physician responses. And this was GPT 3.5 last year. Well, then you think, fine, its accuracy is one thing, but how about empathy? After all, humans are empathetic, and machines would stand no chance as far as empathy of these answers go. So they also had the empathy aspect of these responses from both the computer and the human physicians compared by expert physicians. And this was their evaluation. The responses from ChatGPT were way more empathetic than human doctors. This was surprising. Actually, they actually give in that paper some examples. That makes sense because they had some, we tend to be busy humans, right? And we'll say, look, that spot on your skin, give me a break. It's not going to kill you. On the other hand, GPT might say, I can see why you're so concerned, right? So that response just comes across more empathetic, right? Anyway, so is this going to take our jobs? And what's going to happen when there is GPT-10, right? We'll have more discussions about that. But this was the summary of that research published in UC San Diego today. The study finds ChatGPT outperforms physicians in high quality and empathetic answers to questions. So, we should stand up and take notice. I'm switching to now how these things work a little bit. I'll have a lot more detail coming up, but on language understanding. Because this AI is not image understanding, which, there was most of discussions around AI up until recently has been about image recognition and, how mammograms will be read better than an well-trained convolutional neural networks. But this GPT is all about language understanding, right? So let's take a look at this and see what is this thing about language understanding. A word duck. When you see this word, what do you think? Well, you might tell me, it really depends on the context, right? Just a word doesn't mean much. But if I said that word belongs to this sentence, where we say we saw a duck swimming in the lake, clearly this is what you're thinking about, right? On the other hand, if the duck is part of this sentence, Bush ducks as one of Al Zaidi's shoes flying over his head. Then you think about the 2008 unfortunate incident in Iraq, where a journalist literally threw shoes at President Bush and he had to duck. I met President Bush last week. We were having some fun about this. Okay, so let's do a fun exercise. See if you can. So please pull out your smartphone if you have it. And you can start typing a message to anyone. You can type to me or anyone that you'd like to type to. Type these first two words this morning. Just type those two words. And then what I'd like you to do is 3 words are being recommended by Apple for you to pick from underneath the text. Just pick the middle word. Pick the one at the center, the 3 word, right? That it is recommended. Repeat that. Just keep selecting the middle word 20 to 40 times. And see what it automatically fills in your text message. Is it clear? So keep filling the middle word like multiple times. Just keep selecting. Who wants to read the result? Matt, do you want to go?
This morning, I will be there for you to get the money, to get the money, to pay for the money.
Okay. So anyone else wants to read theirs?
This morning was the best time of my day and my year of high expectations.
Okay, so Apple's doing an autofill algorithm with AI. If you read it carefully, many of you probably think this is like rather garbage. First of all, sentences don't make much sense. They feel like sentences. And then it has nothing to do with your, what you would have typed. This is what they're recommending with AI for you to pick. The one in the middle is the highest probability word that they say you should be picking. So it doesn't work very well. What do you think is the algorithm they might be using to predict this next word? Well, it turns out this also goes back to Claude Shannon. So Claude Shannon, this is in 1948, he published the first information theory of language, and he came up with an algorithm to predict words. So given a series of words, what should be the next word? And he called it n-gram. Essentially, n-gram means pick the number n. If the number n is 3, then you're going to say, what's the third word given a pair of words that is most likely to occur? How do you know that? Well, train the system with a whole bunch of text. Let's say, 10 books or 100 books or all of the text on Wikipedia. Train the system on a statistical model to say if those 2 words appeared, what is the statistical probability of the third word happening? Of course, you pick the word that's probably going to be the highest probability. Here's an example. Zurovsky here at Stanford had a project where they picked the Berkeley Restaurant Project language corpus. It's a simple project. The database had 9,000 something sentences. And he did a bigram analysis. Simply, if there's a word, what's the word that appeared most in this data set after that word? So you pick if the word is picked to be I, what's the word that most followed is 1? The word that most followed after that is 2. Then eat. So just keep reading. I want to eat Chinese food. That makes sense, right? But if you keep going, I want to eat Chinese food, lunch spent. Doesn't make no sense. Kind of start to become garbage, which is what happened with your autofill feature we just played with in Apple phones. So it doesn't work very well. Well, it turns out, if you do 4-gram, means I'll say 3 words, and see what is the word that's most likely after the 3 words. In this case, for example, if my training corpus is this, and I want to see, what is the probability of house appearing after the 3 words? It's 25% from this limited training corpus, right? In any case, people tried with 10-gram and 20-gram, hopeless. It doesn't work very well. And it turns out all this changed in 2017. So a team of Google researchers, people think this team was led by Ashish Vaswani. it turns out they randomly picked the order of the authors in this paper because everybody equally contributed to this paper. And this was the paper where they laid out, let me just call it what it is, a smart autofill algorithm. And they called it transformer neural network. And this was the architecture for that neural network, which I'm going to tell you a lot more about. So for now, just know that this is what, when I said 1.8 trillion parameters, this is the architecture of that neural network that's driving, that's underneath that model. And each of the modules here that I'm going to talk about, each one of them is a giant neural network with hundreds of billions of parameters. So I'll talk more about that. But essentially, this paper was published in 2017. And as of yesterday, when I looked at it, 132,000 citations of the paper, hugely popular. Entire GPT, Gemini, Claude from Anthropic, and Mistral from Mistral, all of the, and Meta Llama, all of the language models today is using transformer models. So if one computer science work paper had an amazing impact to the rest of the world, this is likely going to stand the test of time. And we'll see in the years to come. Because
why did Google put it in the public domain?
That's an amazing question you asked. So I'll give you a couple of comments on this and we'll come back later. Google at the time, Google Research, part of the research unit, they were completely open to just go publish their papers. And their idea was that if you have smart algorithms that are published out and developers start to use them, it's great for Google technology, Google Cloud, and computers and everything. And likely, Google will also adopt it in their product. And the challenge was to run faster than everybody else, an open ecosystem. However, what happened, and there's a lot of interesting analysis going on right now, Google was not the first to completely capitalize on it. The company that capitalized on transformer neural network is who? OpenAI, right? They came up with ChatGPT, and then it was like a mad rush for Google to catch up, even though they invented it. Turns out they were also conservative because these AI models make mistakes. We'll talk about that. Hallucinations. And Google has a lot to lose. If you search something and then it comes up with a stupid answer, likely you're not going to forgive Google. But a startup like OpenAI, you're going to forgive them, right? So Google had to change. In fact, yesterday I was watching an interview that Sergey Brin gave. He said, yeah, Google was conservative. They had a lot to lose, and they were not moving fast enough. He personally came back to Google and spending every day at Google to try and change this mindset. He's thinking, what happened to the Google that I was part of that was a startup? Right? Today, startups are eating our lunch. So suddenly it just changed. Google went through a big reorganization. They had acquired DeepMind in UK, London, and they combined Google Brain team, Google AI team, and DeepMind together to try and create one fast organization to go after this. We'll discuss more if time permits. For now, though, for you to take away, the GPT in ChatGPT stands for Generative Pre-trained Transformer. That's the architecture that Google published. Essentially, it's a giant neural network trained to predict the next word. That's it. There is nothing more to it than that. What is the next word? So rather than an n-gram that Claude Shannon architected in 1948, this is a giant neural network doing the predictions. A prompt for ChatGPT. By the way, this one I borrowed from my December work when I was supposed to come here and present in December last year. So this was still with ChatGPT 3.5. I said, write a 50-word annual update that the head of Stanford Otolaryngology, was that Rob, you or Tina at the time? Right after, okay, so the head of Stanford Otolaryngology could have sent to the university president at the end of 2020. This is the prompt I provided, right? And the 3.5 produced this short letter. Dear President, in 2020, our department thrived amid challenges. Our team conducted groundbreaking research, embracing telemedicine. Despite the pandemic, we achieved unprecedented success, grateful for the resilience, looking forward to a brighter 2021. So you can see that in writing this, the system had all of the intuition about what was 2020. And the short note from the department head to the president baked in the essence of 2020 and summed it up, made a lot of guesses about what the department head might have done with the faculty colleagues. Pretty amazing. Of course, then I challenged it, and again, this was December last year, only GPT 3.5. Write a poem about our department. Total 8 lines, about 6 words per line. And then I gave it a bit more challenge. Start with the words in the world, end with the words, what a delight. And I'll share this with you. It's pretty amazing if you read it. It's got all of the themes in the world where silence surrenders, Stanford's otolaryngology healing renders, symphony of care, notes so bright, ears rekindled, embracing the light. In the realm where wellness takes flight, with Stanford's touch, everything's right. Hearing restored, troubles take flight, oh, such a joy and what a delight. Well, and then last year has been all about video generation. This was from 2023. Will Smith eating spaghetti was created with stable diffusion. How many of you watched this video? So this was 2023. Just watch this stable diffusion created video of Will Smith eating spaghetti. Okay, you all admit, well, it's like there's nothing too inspirational about it. Give it a year, and a year from then, look at the quality of the video now. Just in 1 year. But look at the photorealism and the actions and the expressions on the face and compare that with 2020. Move. How many have seen OpenAI's releasing their video generation capability with the program they call Sora, OpenAI Sora? So this is one of their clips, completely AI generated. The prompt that they provided was a lady walking in the streets of Tokyo. That's it. Everything else made up, and the entire video, the way the perspective changes. And you don't have time to go through the whole thing, but if you they zoom into the face. Anyway, I will send you the link for you to watch it. 1 year, just 1 year in video generation, audio video generation. So I'm going to switch now to hopefully 10 minutes of discussion about how do these things work. Again, it will probably take me like, in a class, we typically spend probably 2 hours on the math of each of these modules, but I'll try to do that in 10 minutes. It's essentially an ensemble of giant neural networks. I've been using this term a lot, giant neural network that mimics the human brain. But whenever I say that, I'm an engineer, I always follow up with this, reminding you that we don't really know all of the ways that brain works. We have simplified the model of a neuron, and the artificial neuron, the building block of the neural networks, are somewhat computing like the simplest copy of a neuron. You have signals coming in through dendrites, getting multiplied by different weights, which are getting trained with data. You have weighted sum, and then an activation function that modifies it, a nonlinear function. We think that's a crude estimate of how the neurons work in the brain. But I like to remind ourselves of Emerson Hughes said in 1938, he's a professor at Carnegie Institute of Technology. He said, if the human brain was so simple that we could understand it, then we would be so simple that we couldn't. How's that for a twister, right? Basically, I said, look, we don't really don't understand, and we'll never understand all the ways that human brain works. But that said, I'm going to take the leap of faith, and I'm going to say, yes, we know fundamentally how we can do a computational module that can copy the ways that human brain performs learning and then inferencing. So let me come back to this architecture diagram that I showed you. And what I'm going to do is I'm going to walk through this. And my goal is this. When you walk out of this talk, you'll be able to go have a coffee chat with people and explain how Transformer works. How's that for a goal? Right? Pay attention. So first, I'm going to talk about the embedding Embedding is essentially a module that transforms words into vectors of numbers. Tokens, by the way, you all might think, I hear this word token. What's a token and what's a word? So essentially, the early versions of language models used to treat the entire word as a word. Stanford would be Stanford, Jackler would be Jackler, Stankovic would be Stankovic. But then what happened? We realized that's not a good way. Because what if there's a spelling mistake? What if Stanford, somebody replaced N with M and the entire Stanford's gone? We need to understand. So we broke up some of the words into smaller chunks, what we call the token. Roughly speaking, there is 33% more tokens than there are words in a corpus of text, right? That's why 13 trillion tokens resulted in 10 trillion words. So the first module then is to take words and convert them into numbers. Let me just tell you, this thing I'm telling you, this embedding that I'm going to tell you how it works, is a giant neural network in itself that gets trained. Okay, next. You look at then, by the way, this is done meaningfully. You don't assign arbitrary number to a word. You likely want to assign smart numbers to the word such that words of similar kinds should have shorter distance to each other. Likely Stanford should be grouped with MIT and Oxford. And then if you say Apple, and what do you group Apple with? With orange and banana or with Microsoft and Google, right? Something to, we don't know. So you gotta see in trillions of tokens, if we train the systems with, what does it come up with, right? So we'll see that exercise. Next thing, you want to encode the order of information in a sentence. Otherwise, you'll get garbage like what Apple phone just produced, right? In an n-gram model. So we'll see how that works. Next is, this is one thing that you should take away. The term was in the headline of the paper, attention. Remember that paper title was, attention is all you need. That was the title of that Google paper. So attention is the heart of transformer neural network. This was the big breakthrough. This is what differentiated this transformer neural network from all other autofill algorithms. It said, what word in that sentence I should pay attention to? What is most relates to? And they came up with an algorithm for that. And I'm going to tell you how that algorithm works. Encodes the relationship between words. And then the last layer is a vanilla feed-forward neural network that we have been talking about for years and decades now. So the result of all this is the determination of probabilities for the next word. Okay, so that's all there is to 1.8 trillion parameter GPT-4 model. So let's look at how things work. Let's look at the word embedding first. So remember, the challenge is that you need to be able to understand it so you can explain to people over a cup of coffee. So let's deal with, let's say, two-dimensional words, vectors, two-dimensional vectors. So we have a task here. We'll say words are nothing but two-dimensional vectors. They have an x-axis and an y-axis. For fun, let's say that we looked at these words, and they are man, woman, boy, and a girl. And what we learned from this is that, well, it looks like two axis systems that would most aptly describe the orthogonality of these four words is age and gender, right? Those are the two most relevant dimensions that will be relatively orthogonal to each other just by looking at these four words. That would totally change if I give you 100 words. You might come up with other axis systems, right? So then you might say, well, boy should be lower in age, and let's say gender somewhat on the lower number. Girl, then would be lower in age, but higher number. Then man should belong here and woman should belong there, right? Pretty straightforward. And then we would say, well, let's add a few more words. Where should they go? If I said child or infant, gender neutral, I didn't tell you boy or girl, you said they should be somewhere in the middle, but lower in age. If I say grandfather, you would say, well, that's older than the man, but on the lower because it's a guy. So we put it on the left. Following the logic, right? This is a word embedding algorithm we just came up with, right? And here's the thing. If we, instead of handcrafting it, we train this system to come up with its axis systems orthogonality by itself, by looking at and learning how do humans treat these words in a large corpus of text. Then we could say, ask it a question. We'll say, well, now you tell me, where should these other words go? The ones in light blue. Where should grandmother go? A well-trained system that's been trained with this dark blue, they would automatically place grandmother here because it's a well-trained neural network, right? Well, so that's exactly how things are done. Now we could say, let's make it more interesting. Instead of 2 dimensions, let's add a 3rd dimension. And the 3rd dimension would be royalty, right? So you could say, well, the boy is on the lower royalty, and the prince would be at high royalty. Similarly, woman and queen, man and king. So suddenly, by adding another dimension, you're getting more sophisticated here, right? So, question. How many dimensions do you think there are in vectors of GPT? The words are represented by not 2 dimensions or 3 dimensions, but 200 dimensions. It's a 200 dimension vector. So I can picture that, image that, but we could you can extrapolate. You can say, well, if 2-dimensional words are 3-dimensional words are like that, we can draw 4-dimensional. But there's a 200-dimensional. Every word is represented by a 200-dimension vectors in GPT. So that's one of the things before I show that a large model. The thing that came out of it, this like it might make you concerned here because the math works like this. If it's a king, so it's this 3-dimensional vector for king, and then you look at what was the 3-dimensional vector for man. Take the manhood away from the king and subtract it. That's king minus man. Let's add that to the woman. It turns out you get queen's coordinates. So there is a logic to this thing. It's deducing relationship between words from the way that we treat these words in a large corpus of text, such that you could add, subtract. So that's the beauty of converting words into vectors, because you could do all kinds of mathematical operations, right? So that's interesting there. And so I don't have time, so I'm going to skip. I'll send a link. There is a live module you can go to. What did they do? This is a Google TensorFlow open visualizer where they put 10,000 words with 200 dimensions each. But then using principal component analysis, they project that 200 dimension vector into a 3-dimensional space. And you could play with it. You could go to that link and play with it. I put Stanford, and immediately Stanford came up in the 10,000 words. And you can see cosine distance. Stanford is closest to the word university, followed by Berkeley, followed by Harvard. Kind of makes sense. So just by this first layer of neural network and this module that's all embedded, you already established a pretty good relationship between words, right? Okay, so that was the embedding. I'm going to jump now to this attention, which is the biggest breakthrough, right? So what is attention? The idea of attention is we want to see the relationship between words. So much of why did the chicken cross the road? So the sentence I picked is the animal didn't cross the street because it was too tired. And then I took an example of a well-trained attention neural network. And we look at the word eat. What did it pay most attention to? Well, think about this. If I show you this sentence, the animal didn't cross the street because it was too tired, and I ask you, what do you think most likely eat is referring to? You say, that's so simple. Of course, it's the animal. Remember, for a computer program, it's not intuitive at all. You got to program the damn thing. And you saw how even Apple's autofill program doesn't do very good, right? So this is the result of an attention model that does a very good job, which is why GPT is standing out in terms of meaningful text, not just meaningful, 40 words, but poems, a letter from Tina to the university president. It's amazing, writing a book for you, probably. And that's, this is what is this. So eat is attending to the animal the most. The thickness of the line represents the weight of the attention is paying to that particular phase of the sentence. So that's the output of this module. So how does it work? First, don't have to memorize this equation. The reason I'm first showing you the equation is because I'm going to use it to draw some intuition. Attention, again, is multi-100 billion neural network. At the core of it is basically a very simple equation. It's a function of three different matrices. They're called queries, keys, and values. Okay, one way to remember this thing, the query, key, and value. Query is just that, it's a question. Key is the key to the vault where the answer to the question lies. You have a key to it. And the value is the answer itself. So think about it. I ask you a question. That's the query matrix. And then you need a key to find answers to it because it's locked in a vault. And you open the vault, you get the value. So those are the three different, this is the intuition behind the math because, it's like the math can get complicated. Softmax is a function that normalizes numbers between 0 to 1. That's all it is. Like because when you end up multiplying three different matrices, Q, K, transpose, and V, divide by square root of the dimension of the vector. So for 200 dimension vector, it will be divided by square root of 200 because you want to keep it relatively independent of what vector size you pick. So you normalize with the vector size. You further normalize it to numbers between 0 and 1. And you'll see why. So that's the attention. But here is the intuition behind it. These X's are the vectorized words. We just discussed that, right? The embedding vector. So you got a 200 dimension vector for a word. That gets multiplied by a weight matrix for Q, and the result is this query. The same word will be multiplied by yet another matrix, and that would be a weight matrix for the key. The result of this multiplication would be the key, and similarly values. Well, where are all these things coming from? We saw where this is coming from. This is coming from the word embedding neural network. It turns out these weights, gigantic matrices. They're simply set random to begin with. And then this attention module is trained, and it learns what sort of weights are the most relevant to a particular question, what sort of key is needed, and what the actual value is. You don't worry about it. The software engineers don't have to worry about it. Just train this thing with more data, that's it. Sit back and relax. Write your matrices, decide the dimensions, put them in a neural network, train with all languages in Wikipedia, and see what comes out. It made our job, software engineers' job, so easy. Today I'm not going to talk about hearing aids. Same things. Like we used to signal process based on the types of sound, what should be the amplification and stuff. Today we don't do that. We just use neural network. So it'll be a conversation for another day. But once you've done that, then here's the thing. Life is not as easy. Another stroke of genius from the 2017 paper was not just attention, but multi-headed attention. What they said is attention establishes relationship between words, but there is another aspect to that relationship. What am I looking at here? Is this a medical related question? Or is this a fun question? Is this a joke? Is this serious? Am I asking about stock trading? Or is this about, there are many other dimensions to a sentence. If I tell you this is a sentence, what this means, you might say, tell me more. What is the context of this question? If I say, get out of here, you might say, well, I'm asking you to get out of here. Or you'd say, what was the tone of the thing? Might be, get out of here. That means, no, you don't really have to get out of here. So there's a lot more nuances in human language, which we want the system to learn. So they basically, all they did is facilitate the multi-headed attention. So instead of one, there are multiple parallel things. And the result is a concatenated attention numbers, between 0 and 1, because you normalized it, and added back to the embedding. Now think about what's happening. Embedding itself is a giant step forward from the n-gram models you saw in grouping words by their meaning, trained based on corpus. Now you're adding on that modifiers based on the relationship between words and the context and things. This is what is the magic for GPT. All right, last stage is the feed-forward neural network. That's the easiest thing. We already knew that. And that's basically just a vanilla series of feed-forward neural network. I'm showing you a few, but this is itself several hundred billion neurons. Each of them is a mathematical unit which takes all these inputs coming into it, multiplies by weights. Those weights are also learned from, there's so many learnings involved, right, in making sure that every layer is learning from the data we are training it with, which is why the training data set is important, which is why the 10 trillion words needed. And then at the output of this entire 1.8 trillion parameter neural network is the probability of that word, and it does a much better job than N-gram model that we just played with. So with that, I want to spend like 2 minutes on the issues, and then maybe we can have some discussion. Issues, limitations, and the future. What do you think is the most biggest concern that we all of us read about and we talked about it? What's the biggest issue, despite all of its amazing fits? What's the biggest concern with these AI models?
Hallucination.
Yep, you're totally right. Hallucinations. In fact, I played with it myself. And they're just getting better by leaps and bounds. But back in 2022, when I tested, I asked the question, who was the first human athlete to have crossed English Channel on foot? It actually gave me an answer. So it was hallucinating, right? If you ask it today, it will say, humans cannot walk on water, sorry. Right? It's getting better. So hallucination is getting better, but it is still a concern, which is why you got to pay attention. You got to rely on it, right? It's not going to, for those of, many students I advise when they're writing papers, they will use AI models a lot. But one area they cannot use it for, many of them they cannot use for, is suggest some reference articles for this paragraph. It just totally hallucinates. Perplexity does a better job. GPT gets it wrong all the time. It's actually more concerning. It gets it wrong in a way that is misleading. It will likely, say this paper on cochlear implant, author Tina Stankovic, and it doesn't exist. But when you look at the author and look at the paper, you think, oh, I can see it, probably true. But when you search, the paper doesn't exist. So it is a real concern. Costs. Sam Altman, the CEO of OpenAI, publicly said to train GPT-4 cost him $100 million. And that's on top of probably $500 million to $1 billion of cost in hardware. Today, the biggest models that are getting trained, these people talk outside, $5 to $10 billion of investment that's needed just to have the ecosystem, the hardware infrastructure, and then the trainings. Expensive. Well, now, the fun part of it, I looked through the numbers and did some calculations. How about power and water consumption when we are using ChatGPT? So what I did is I assumed if you have a productive session with GPT, not casual questions, but you're doing a research, you might be having maybe 10 to 50 questions you might be asking it. It turns out that session is equivalent to keeping a 60-watt light bulb on for an hour. A single session with ChatGPT is consuming power. There are other things like data centers around the world. They're just the computers that run these AI models. They consume between 200 to 300 terawatt hour. That's 1 to 2% of the entire world's energy consumption. 10 to 15% of them are AI. So 20 to 30 terawatt hour. Compare that with an entire country of Ireland, less than 30 terawatt hour, right? And here's the thing about Ireland I looked at. Interestingly, Ireland is a place where we've got a lot of good commercial terms. Companies are extending their data centers there. It turns out almost a quarter of their energy consumption is because of AI. Right? Okay, one other thing, you don't think about power consumption. So I wanted to look at it. One session with ChatGPT, gulps 500 milliliters of water because the water is used to cool the servers that are processing those things. So you are consuming power, you're consuming water every time you're interacting with ChatGPT. So we should be responsible. Question is, why don't they charge us? Well, $20 a month, those of us that pay, right? You get indefinite use, but many of us can use it for free. Turns out the Silicon Valley model, right? Get developers, establish your capabilities, money will come later, right? People will pay for it and figure it out. So to end it and wrap it up and open for discussion, so do we think AI will just augment us or replace us? As professionals or doctors in the room, what should our approach be at the moment? And I want to show the last slide and then open up. I really like this one. This is from Karim Lakhani at Harvard Business School. He said in an interview in August of last year, AI won't replace humans. He made a definitive statement. It won't replace us. But what will happen is humans with AI will. That means those of us that do not use this as a tool will be replaced by those that do. And that applies to everybody. That applies to CTO of a company like me. My team is not using AI to improve products. Other companies will make better products. Professors who are teaching, students who are writing essays, they should be using it, just like calculators in the 80s, right? It's a tool that you should be using to get better at things. Well, a lot of questions about cheating. What happens? Well, you'll not be a good researcher if you do. And the world will figure it out eventually. You might get an A in Rob's and my class, but then you won't be very much of an engineer that I'm going to hire in my company, right? So that was my last slide. Do you have a hard stop at 8, or can we go a couple of minutes of see if people have any questions?
Maybe 2 minutes.
Okay.
Because residents have another session.
Sure. And if you have to leave, I'll understand that. Any quick comments or questions?
Well, thank you for a fabulous and really inspiring lecture. I think we could have an hour of questions. It's very obvious that we need to invite you for a second round.
If I do come back for a second round on this topic, I'll talk about applications, like how we are using it in hearing devices and maybe pick a few other medical device applications and medical applications where with this background, we can talk about applications. But today I want to really spend the time on understanding of how it works and a little bit of motivation.
We are so grateful, Achin, that you're part of our department. It just expands our awareness, our capabilities, and our knowledge. And thank you so much for really inspiring talk.
Thank you very much.